Lucky everybody, good morning. So we have a short day, 3 beautiful talks. We're kicking off with Yunfeng Jiang from Southeast University on I think, a fascinating topic which somehow combines string theory, quantum circuits, dynamics, everything. So take it away.
Thank you very much. Good morning, everyone. I'm Yunfeng Jiang from Southeast University in China. So this is the corresponding country. And so first of all, I would like to thank the organizers for the kind invitation and for giving me the opportunity to talk here. It has been a wonderful workshop. I've learned quite a bit from the talks and the posters for the past 2 days, both from experiments and from theory. So my topic today is about quantum circuits, which has been mentioned in the previous talks, but I hope I can give a slightly different perspective, in particular from integrable models and from mathematical physics. So if you haven't heard about or learned about algebraic geometry, don't be scared by this title. I'm going to explain in detail. As long as you know some basic linear algebra, you should be fine. Okay? It's not going to be crazy difficult. So this talk is based on the following papers. It's mainly about this last one, which appeared a few months ago on arXiv. And the techniques that we developed to compute these exact correlation functions are developed in these previous papers. Our main collaborator is Yunfeng Jiang from USDC, and also Zoltan Beinok, Jasper Jacobsen, and Rafael Nefovici. So we all know that quantum computation, of building a quantum computer, is a big dream. And it's fair to say that this is building a fault-tolerant quantum computer in general is still a dream, and it's in the distant future. So nowadays, we are in the so-called NISQ era, which effectively means that people nowadays with technology can effectively control 10 to 100 qubits, say in a one-dimensional ring. And this, we have heard about these talks. And so a natural question is, what can we do with this 10 to 100 qubits? And as we learned from the talks in the previous days, that one exciting thing we can try to do is to simulate quantum many-body systems and to learn about new things. And among all the quantum many-body systems, there's one type which is very special, and this is the integrable systems, for example, the Heisenberg spin chain. Now, they are interacting quantum many-body system. They are not free, but they have so many conserved charges, which usually make them exactly solvable. The history of a quantum integrable system has been quite long. If we count Bethe ansatz from 1931, where Hans Bethe solved the spin chain, it's 93 years. And for a very long time, at least for 50 years, these models are usually considered to be some toy models, which people who are interested in them are mostly mathematical physicists, because these models are exactly solvable and they have very beautiful structure. So you can play a lot with these models. But nowadays, we are a bit more lucky because with the development of quantum technology, many integrable models can be realized on some real-life experiments. For example, you see some integrable models like spin chains in certain quasi-one-dimensional quantum material. And also, you can simulate integrable spin chains and other models by cold atom and Rydberg atom experiments, which we heard some nice talks. And also, we can model integrable models by quantum circuits. And so this is also the topic today. So combining quantum computation and integrable systems, a natural question is, can we combine them and do something, like in this area? And when you think about this problem, you have 2 very natural thoughts. Thought one is, okay, maybe we can use this quantum computation and these quantum platforms to simulate integrable models and learn about something new. So for example, a recent example is that people can use quantum circuits to simulate Heisenberg spin chain and learn about quantum transport. And they find some it was found there are some KBZ-like dynamics, and in this experiment, it was found that okay, there are some discrepancies. So it's not exactly KBZ, and this is still a very active research area. So this is one example where we can really use this quantum computation platforms to learn about something new about integrable models. Or you can think that, okay, can integrability do something? At least be a little bit useful for quantum computation. So what integrable models can offer are analytic results. Analytic results for quantum many-body system. So I want to emphasize that for generic quantum many-body system is very hard to solve, and getting analytic result is extremely difficult. Now for integrable models, I'm not saying it's easy, but it's possible to obtain analytic, highly non-trivial analytic results. And if you have these results, you can calculate as accurate as you want in principle. And this can be used to do error mitigation for these quantum platforms. So I learned from Derek, there are many ways to do error mitigation. And the one possible way is to compare the result of simulation with some exact results. And then you can try to optimize your circuit. Okay, so this is what one of the motivations that we have in mind to do these analytic computations. So another motivation is that purely from integrability point of view, this quantum circuits is a new type of playground for integrable models. So we can imagine building a new type of integrable models and study them on this quantum circuit platform. So this is also exciting for integrability. So that's another point that we want to study this integrable quantum circuits. Now, with this motivation, then I'm going to introduce to you what is exactly the model we want to study and what are the observables that we want to compute exactly. So this is the brickwork model. It has been introduced in the talk from Professor Houghton's talk. And this is, so we build this brickwork models by some fundamental two-side gate. So this is the two-side gate that I'm considering. You have two incoming legs and two outgoing legs. So each leg is a qubit. And you can represent this two-side gate as a 4x4 matrix with parameter alpha and this phi. Now, I want to extract out some trivial global factor, and then write this U gate as some R-check gate. And this R-check gate is parameterized by U and eta, and then you have the CU and the VU, when these two sets of parameters are related by this change of variable. Now you might wonder, why do I want to write everything in terms of R-check? Because if you're from integrability, you recognize immediately that this R-check satisfies the Yang-Box equation. So actually, it is a standard UQSL2 invariant R matrix. And it's the R matrix of the Heisenberg XXS spin chain. So this means that this circuit, if I build it using this R-check gate, it has some built-in integrability. So from this point of view, I will call this kind of model integrable quantum circuit. And then what do? After I have this two-side gate, I start to put them together and form some brick wall. For example, in the first layer, I just multiply these R-check gates like R12, R34, and so on. I call this U odd, which means this odd layer. And then in the second layer, I have a product of R23, R45, and so on. This will be called R even. So every two layers will be a cycle, and then I can repeat this cycle several times. So this is like a time evolution. So in this blue direction is the time evolution direction. And the time evolution operator is this U, which is a product of U odd and U even. Okay. So I want to comment that this is not the first time that people consider this type of model or this type of a brick wall. Already in the 90s, people from statistical mechanics, for example, Young and Buster, already studied this specific lattice model. This is called the 6-vertex model on the light cone lattice. And actually, from statistical mechanics point of view, typically you care about this partition function, and you want to take the thermodynamic limit, you want to see whether there are phase transitions, and so on. So in more recent years, this is also proposed as a realization of chaptalization of XXS big chain, first by the Prosen group. And also, there's a nice work from Mariushi and also Masahito, also my colleague Ryo Suzuki in Southeast University. They investigated also this circuit, but they mainly focus on conserved charges on this integrable circuit. Okay, so of course it appears more than one times, but in different contexts, people care about different problems. They ask different questions, and so the thing we want to investigate today is about some natural observables on this circuit. So what is natural observable on this circuit? So it's about, is this correlation functions, or what we call correlation functions. So it's the following thing. You start with this qubits. So you start with a state where all the spins are up, say, or in terms of qubits, all the states are 0. And then you add a string of operators, spin flipping operators, which is sigma x. So for example, in this diagram, this would mean the first 4 sites will be state 1, and then the rest will be state 0. So in this situation, you have something called a domain wall state. So basically, you prepare this domain wall state, and then you evolve it using this U operator. You evolve it n times, and then you project out by a similar domain wall state. But this domain wall can be, in principle, in a different place. Okay, so this is what we call a correlation function. You build a domain wall state, you evolve it, and then you project out. So this is amplitude, and this thing can be easily measured on quantum circuits. So our goal is to compute this thing exactly. So why this is a non-trivial problem? Because this R check, as I said, depends on 2 parameters. And then if you just do it by brute force, this is going to be a very big matrix. And then you want to compute this matrix element. So what is really helpful here is that we have integrability. So remember, this R check gate, they satisfy Yang-Boxer equation. So due to this fact, we can compute this correlation function using a technique called Bethe ansatz. Basically, the idea is that because of our check is satisfy Yang-Boxer equation, so this evolution operator U can be identified with certain transfer matrix. And this transfer matrix can be diagonalized by the Bethe ansatz. So I don't want to bother you with the details, but essentially this means there's a systematic way to construct eigenstates of this operator, and then you can calculate the eigenvalue. So each eigenstate is parameterized by a k parameters, which I denote by uk here. And they are called rapidities or beta roots. They have to satisfy this equation, and this is called the Bethe ansatz equation. As you can see, it depends on the parameter u and eta. So the rule of the game is the following. After using the Bethe ansatz, you need to solve this equation. You solve it numerically or analytically. Then in principle, each one of this solution, you can plug in here, and then you obtain some number. And this is the number of the eigenvalue of this operator U. So that's what you do if you use Bethe ansatz. Okay. So as I said, if you compute this thing by brute force, what you need to do is to first build this very big matrix analytically, and then you take out this specific matrix element. Now, if you use Bethe ansatz, what you can do is you can insert here a complete set of beta states. And then you will have this eigenvalue tau to the power of n, and then the rest will be some overlap between this state and the beta state. And this is what I will call W. So they have, so we know their form explicitly. These are basically some rational functions or trigonometric functions of these beta roots. So we know them explicitly, but it's a little bit complicated, so I just don't show them. And so use Bethe ansatz, how do we compute this correlation function? So we need to solve this Bethe equation, as I emphasized, and you'll find many, many solutions. So you need to find all the solutions, because here we are inserting a complete set of Bethe states. So you need to find all the solutions, plug in here, and compute every term, and then take the sum. Okay, so this sum means the sum over all solutions of Bethe ansatz with Bethe ansatz equations with fixed L and K. So here this L, twice L is the number of qubits you have. Okay, so that's our task. I hope it is very clear. And it's also useful to consider the Fourier transform of this correlation function. And in the Fourier transform in the Fourier space, it also depends on this WUN and the tau UN. So here I want to comment on something. So I want to say that in this quantum circuit context, the question we are asking and the problem we are dealing with are slightly different from traditional condensed matter or statistical physics. So if you deal with statistical mechanics, typically you care about thermodynamic limits. And in this limit, some simplification happens, because in a thermodynamic limit, you don't need to consider all the solutions of Bethe ansatz equations. Typically, one eigenstate will dominate. One or few eigenstates will dominate. And you just need to focus on the eigenstate, which is the largest. Okay? But here we are dealing with a finite number of qubits, say for 10 to 20, or even slightly more. So here, this is not the thermodynamic limit. So at this length, thermodynamic limit is not a good approximation. So to get exact results, we really need to find all the solutions of Bethe ansatz equations, and we really need to take this sum. So something which is well known for the experts, but probably not emphasized a lot, is that the Bethe ansatz equations are not easy to solve, as you can probably guess. So you need to develop some special techniques to solve these equations. And then there are also all kinds of subtleties, like not all the solutions are physical. So you need to get rid of these solutions also. So this is a non-trivial problem we are dealing with. And usually you can only solve the Bethe ansatz equation numerically in a generic case. And then you find this numerical solution, you plug in this sum up, you get a bunch of numbers, and then you sum these numbers. That's what you can do. Now, what I want to claim here is that using the tools from algebraic geometry, we can perform this sum analytically without any approximation, even without solving these equations explicitly. And that's the tool that I'm going to introduce in the next one.
About this problem number 3, does it mean that you get more solution than the dimension?
Yes.
Oh, okay.
So this is called a completeness problem.
Yes, I know. Yeah, that's I know, but you get more.
You get more. You can definitely, yes. So yeah, if time I will comment on this point. But my goal today is to tell you how to do this sum. Yes.
So in the calculation of correlation functions, you inserted the complete set of Bethe state, right?
Yes.
So I'm not sure whether the Bethe states really, how to say, Bethe states are the completing the full Hilbert space, because in the XXT case, we usually need a descendant from the Bethe states. So a Bethe state are
good point. Yes. Indeed, in the XXX case, what Bethe ansatz give you is the highest weight state, or the primary state. And then you also need to take into account the descendant states. So in XXZ, in XXZ you have more solutions, and because SU2 invariance is broken, so you don't need to take this into account. But yes, in reality, in XXX, we do need to take into account descendant states. But once you know the overlap formula for the primary states, it's rather easy to deal with descendant state. You just need to take some of them to infinity. Yeah, thank you. Yes. So we see there are some real experts in the audience. Great. Okay, so before I introduce all these advanced technologies, let me give you a very simple example, which is a baby version of the problem that we want to solve. So let's consider this problem. This is a toy problem. We consider a polynomial equation, qx equals to 0. And this qx is a polynomial. Now I take a polynomial of degree 5. It's not particularly important. It's just some random polynomial where we have coefficients are rational numbers. And I take a function, which is also a polynomial with rational coefficients. And so the question I want to ask is that I want to find all the solutions to this equation qx equals to 0. And for each solution, I plug in this function f. And then I want to calculate this sum. So this is very similar to the problem of solving Bethe equations, find the solutions, plug in, and take the sum. Okay? So how are we going to do this? Of course, the simplest thing you can do is numerics. So you can solve this equation, qx equals to 0, say up to 25 digits. Because this is a polynomial of degree 5, you can find 5 solutions very easily. I denote them by x1 to x5. And there are some irrational numbers. So then I can plug in these 5 numbers to this f. So this will give me another 5 irrational numbers. And as easy as it is, you take the sum. So once you take the sum, you find something funny going on. You see the sequence 750915, 750915. It's repeating itself. And then if you solve with more digits, you find this sequence just repeat more times. So all this is telling you that the final result want to be a rational number. And this is the approximate rational number. Now, of course, if you do it using numerics, you always have to truncate at some point. So you'll never get this exact rational number. So the question is, can we have some analytic methods which get this number exactly? So I will introduce this analytic method, okay? My starting point is a linear space. It's a linear space spanned by these 5 vectors, E1 to E5. They are monomials. They are monomials in X, so E1 is X to the power 4, E2 is X cubed, and so on. So you'll see immediately why this linear space is relevant. Because we are considering 2 polynomials, qx and then fx, so it makes sense to divide them. So I can say I divide fx by qx, and I try to find the remainder. So this division, so this part is not important because when I set qx equals to 0, this is always vanishing. So what's non-vanishing and non-trivial is this remainder. Now remember that my qx is a polynomial of degree 5. So this means my remainder can be at most degree 4, which means it has to sit in this linear space. So that's why I consider this this a linear space. So this is the remainder, which you can obtain by a simple calculation. Now what I want to do is to somehow find a representation of this remainder in this linear space. So this is a 5-dimensional linear space. So I want to construct some 5-dimensional matrix to this R, which is some kind of representation. So how do you do that? You can take the first vector and then you add this Rx on this vector, which means you take the product of this Rx with this monomial, and then this will be a polynomial of degree 8. So you can divide again by qx and find this remainder, which I call R1. Now this is not important, this quotient, because qx equals to 0 will always eliminate this term. And this R1, as I repeat once more, can be at most degree 4. So it can be written as a linear combination of these vectors, and then you have some coefficients in front, okay? We can do this for each single vectors. I can do it 5 times, and then I can extract this, I can compute 5 remainders, and these remainders can be expanded in terms of this basis again, which gives some numerical coefficients. And this can form a 5 by 5 matrix. And this is called the companion matrix of this function f, or of this function r. And it looks like this. So the first row, I have shown you how to do that. And then you do just a few more rows. So this is a very simple calculation, and then you get this matrix. So remember, in this procedure, all we are doing is polynomial division, and then read off the coefficient, nothing deep, not solving any equations. Then you take this trace. what you find is that, okay, after taking this trace, you've got exactly this rational number, which will obtain approximately from the numerical approach. And if you try to diagonalize this matrix, finding the eigenvalues of this MF, you will find exactly this fx1 to fx5, which are themselves irrational numbers. So basically, the idea is that finding single fx can be difficult and nasty, but taking the sum can be easier because you can see finding the eigenvalue of each eigenvalue can be difficult for a matrix, but taking the trace of a matrix is very easy. So that's the rule. That's the secret why we can do this sum analytically.
Is it trivial that the eigenvalues are fx1 and the fx5? Is it easy to see that the eigenvalues are fx1, fx2, fx?
It's not easy.
Okay.
It's not easy. You need to really use some algebraic geometry to prove that.
Yeah, because I didn't see the proof myself.
Yes, it's not obvious. Yeah. Yes. Okay. So that's the tool we need. I want to emphasize 2 points. First is that the result is exact. There's no need to solve any equations. And second, it's clear from the procedure that we are constructing this matrix that the final result must be a rational number. If you start with 2 polynomials with rational coefficients, then the result has to be a rational number. Okay, so here we are secretly using some notions from algebraic geometry or commutative algebra. So first is this quotient ring, Cx, which is just all the polynomials in X with complex coefficients. And now we can talk about ideal generated by some polynomial. So this is just all the polynomials of this form, Ax times Qx. So if you impose the equation Qx equals to 0, all the elements in this ideal are 0. So it's like the quotient part. And then you can take the quotient space of this polynomial ring and the ideal. This is what is called the quotient ring. So basically, this is the space for the remainders, or this is the linear space that I start with. Okay, so this is called quotient ring. And because it's a finite dimensional linear space, you can give a basis. And the standard basis of this quotient ring is simply given by all the monomials that cannot be divided by leading term of Qx. So our Qx is a polynomial of degree 5. So leading term is x to the power 5. And all the monomials that cannot be divided by this guy is x to the power 4, x cubed, and so on, which is the basis that I wrote down in the previous slides. Now, the key result from algebraic geometry, which is non-trivial, is that for each polynomial, we can map it to a numerical matrix, as I just described. Namely, you do polynomial reduction, and then you find the remainder. You multiply with these monomials, you find remainder, and then you expand. And the dimension of this quotient ring is exactly the number of solutions for this algebraic equation. Okay, so this is what we learned from this baby problem. Now we go to the real problem. So in the real problem, what we want to solve is not this single variable equation, but it's a multivariable equations. And the functions we consider are also non-trivial functions of beta roots. And then, of course, we want to calculate this sum, which is the problem of computing this correlation function. And we need some real algebraic geometry. Again, we have polynomial ring, but this time just in multivariables, say n variables. And you can talk about ideal, but this time it's not generated by a single polynomial, but can be n polynomials, b1 to bn. Imagine this is the equation, b1 equals to 0 to bn equals to 0. This is the equation you want to solve. And then you can form this ideal. It's more or less the same. Once you impose that equation, all the elements in this ideal become 0. So you can take the quotient space of this two infinite dimensional space, and you obtain the quotient ring, which is a finite dimensional linear space if the solution to your equation is finite. And the result we need is that the number of solutions of this system of polynomial equations is exactly the dimension of this quotient ring. So basically, our key strategy is that instead of solving equations, we want to construct this quotient ring. We want to find this this basis for this quotient ring, and then we construct the companion matrix. So that will be our strategy.
I have a question.
Yes.
Yeah, so, okay, I have two questions. So first of all, the Bethe equation that you wrote down.
You should do.
Yeah. The Bethe equations that you wrote down is in terms of Laurent polynomials, right? So would that be a problem when you're dealing with this technical question?
No, you can write it in terms of a polynomial equation. It's a Laurent polynomial, but then you can always rewrite it in polynomial.
Yeah, okay, then they are okay.
And actually, just to be more precise, well, in practice, we're dealing with the Q system equations.
Yeah,
It's not just the BAE.
so it's not just BAE. Okay, that's my second. Anyway, okay.
It's not the base.
Okay, I see. Yeah, because
Yes.
there are physical solutions.
Right.
Okay, good.
For this talk, if I need to talk about Q system, then I need another half an hour. So just let's say approximately I'm solving Bethe equations. Okay. Now, but you see, in the one variable case, it's basically high school mathematics. You do polynomial division. So why do we need some advanced technologies for algebraic geometry? So here I would like to quote the condensed matter physics slogan: more is different. Of course, there they mean a lot of more is different. Here I want to say even one more is different. How to see that? So in the one variable case, if you talk about dividing one polynomial by another, you know what you are doing. You know how to compute the remainder, and there's no ambiguous. Now, consider in the two variable case, let me say, okay, I want to divide this polynomial by these two other polynomials and find the remainder. You can find this. So this 2x plus 1, it cannot be further divided by f1 or f2. So it's a good remainder. But the problem is, you can also write this. And now you have a remainder x plus y plus 1, which cannot be further divided by f1 or f2. This is also a good remainder. So the problem in the multivariable case is that the remainder is not unique. And we are in big trouble because all the procedure we are based on is find the remainder and then construct the companion matrix. But here, even the remainder itself is not unique. So at this point, we need algebraic Bethe ansatz. We need some tool called the Gertner basis. Roughly speaking, this is the following. If you have an ideal generated by certain polynomials, you can do a change of basis. This is something like change of basis in linear space, but it's a very nonlinear change of basis. So you change. So this same ideal can be generated by a different set of polynomials, which I call G1 to GS. And it's so nonlinear that this S doesn't have to be the same as N. Now, among all these bases, there's one type of basis which is very special. This is called Gertner basis. So the good property of the Gertner basis is that if you do polynomial reduction with respect to Gertner basis, you will find unique remainders. And that is proven by the mathematicians. So that's why Gertner basis is important for our purpose. So it's named after the Austrian mathematician Wolfgang Gertner. Actually, this was constructed by his student, Bruno Wuppert, and named after him. So that's why it's important to have brilliant students who can make you famous. Right, okay. So then it's clear what we should do. If we start with some polynomial equations, what we should do is to find the Gertner basis first. And then we'll do polynomial reduction with respect to these guys. So how do we compute it? So this branch of computational algebraic geometry started in the 1970s. And then after so many years of development, there are some very standard algorithms to compute the Gertner basis. So if you are facing very simple equations, you can use pen and paper. You just follow the steps. So there's an algorithm. And if you do with a slightly more complicated case, you can use Mathematica. So there are some internal functions called Gertner basis, which can compute this thing. And if you do something even more complicated than like what we are doing, then you need some more special package, like the singular package. Okay. So suppose now you use whatever method you constructed the Gertner basis, then how do we write down the standard basis for the quotient ring? And it's easy. Now it's the same. you just look at the leading term of all the Gertner bases, and then you find all the monomials that cannot be divided by this guy. That's it. By the way, this is the brilliant student, Bruno Buchberg, of Gertner. So let me give you a very simple example. So this is the same example which I said you don't have a unique remainder. F1 and F2 is here. It can generate ideal, and you can do a change of bases. And these are the Gertner bases, G1 and G2. Now, one thing is that when you compute Gertner bases, you always need to choose an order, because in this game, it's important to know what is the leading term. So for example, here, X and Y, who is the leading term? So there's no canonical order. So you need to pick an order, and then the result will depend on the order that you pick. So in this case, we pick the order X larger than Y. And in this order, this G1, the leading term of G1 will be Y squared. Leading term of G2 will just be X. So you want to find the monomials in X and Y that cannot be divided by these two guys, and you don't have much choice. They can be either Y or 1. This means this quotient ring has dimension 2, which means this equation has two solutions. And this is obvious because Y squared minus 1 equals 0 tells you Y is plus minus 1. And then you plug in here, you find the corresponding X. So it matches. Indeed. Okay. So after we have this quotient ring basis, then the next step is just to construct the companion matrix. And we did precisely like before. We take this polynomial, multiply this quotient ring basis, and then you perform the polynomial reduction, but with respect to Gertner basis to make sure that your remainder is well defined. And then you can expand your remainder in terms of this standard basis again. So in this way, you can construct the companion matrix. So if you want to take the sum over the solutions of something, that's what you do. You take the trace of the companion matrix. You don't solve any equations. And then the companion matrix has this following properties, which is very nice. So this just means that if you have two polynomials, P1 and P2, so then their combination, the companion matrix of their sum is just the sum of their companion matrix and so on. So in particular, using the last equality, you can construct the companion matrix of any rational function, not just polynomial, because here we are dividing P1 by P2, so you can construct the companion matrix of some rational function, and this will be useful for our purpose. Okay, so let me quickly give you an example, which is a slight generalization of our toy model. So I want to solve this equation, F1 equals F2 equals to 0. So now this is a system of equations, and then plug in here and then compute the sum. So from numerical approach, you find that this system has 12 solutions. You can solve them easily, and then you plug in there, you find approximately, this is again a rational number. Now what we do in the analytic approach, first, compute the Gertner basis, and this is what you have. Second, establish what is the standard basis for the quotient ring by looking at, so the leading term here is x fourth, and the leading term here is y cubed. And then you find 12 monomials that cannot be divided by these guys. And then after having this standard basis, you just construct the companion matrix. And it looks like this. You take the trace, you get this number. So that's it. So the whole procedure is purely algebraic and analytic. The most non-trivial step is actually constructing the Gertner basis. And the algorithm is basically still doing polynomial reduction, looking at the leading term coefficient. You didn't solve any equations. And so it is purely algebraic and analytic. So the final result, if you start with a rational number coefficients, is always a rational number. Yeah.
Yes, so for isotropic case, I understand that all the coefficients are rational numbers.
Yes.
But for the anisotropic case, except for very rare cases, I don't know, true to unity or something very special, then you can have maybe all the coefficients being rational numbers, but generically they are just
Generically they depend on Q. And then this whole procedure also works if you have free parameters.
Yes, but okay, so the ultimate reason why this rational number is only for Q is a rational?
This is just a demonstration. So I don't have to deal with rational numbers. You can even do algebraic extension of rational field, rational number field. So
yeah.
So you can deal with equations with coefficients. So I'm not desperate to get rational numbers. This is just a demonstration.
But maybe I'm more impressed if you could get rational numbers.
Yeah, you can.
For isotropic case, I guess you always get rational numbers.
Yeah.
Okay.
You'll see that for generic case, typically because you have some free parameters. So the result will be some analytic expression in terms of these free parameters.
But you can consider such a range that could expanded by Q.
Yeah.
You will get analytical results in Q.
In Q, yes. Then you can take Q to whatever crazy number you want. Okay. So let me now go back to the common circuit problem, which we might already forget. So in terms of beta ansatz, this is what we want to do. Okay. We have an expression in terms of beta roots, which I claim you can write it in terms of rational functions. And we have a set of equations you need to solve, and then you can take this sum. So finally, I'm just showing you some results. So this procedure, you can program it and you can calculate it. So the result is something like this. In the general case, we have this result. So this is the anisotropic case. So this is the isotropic case, where this alpha are some coefficients. Okay. So for the very short time, by very short time, I mean you just evolve it like 1 or 2 cycles. This means some very shallow circuit. For this very short time, what you can find is that for some fixed n, the result is the same for L larger than n plus 1. For example, okay, so this n, this small n, is the discrete time or the layer of your circuit. So if you take n equals to 1, whatever, so L, so as I said, 2L is the number of qubits. So you can take 2 qubits, you can take 4 qubits, 6 qubit, and 2L qubit, they give the same result, as long as this L is larger than 2. And then for this 2 steps, as long as it's larger than 3, you got the same result. So this is basically, physically what it tells you is that the speed of information spreading is bounded. So you have this light cone. And if you take the medium time, say 10, which means you have 20 layers. So as I learned from the experts, if you take more layers, then the fidelity is lower. So what I'm going to show for the next few slides, just take it as some pure theoretical interest. It's useless for common computation at this moment, because we are going to consider a lot of layers. So this is more interesting probably from the statistical mechanics point of view. So you get some analytic expression, right? It's very analytic, but it's a big polynomial. So it's not extremely illuminating to look at them. So instead, we can plot their zeros, because for polynomial, basically it's determined by its zeros and asymptotic behavior. So here I'm plotting these zeros for like a qubit and 2 magnum, and then 6 steps. So it's not, you don't have a lot of pattern here, so you get a bit more zeros. But suppose you take n equals 500, so you take a layer of 1,000, and now you can look at the zeros. You get a huge polynomial, which is of degree 2,000, around the degree 2,000. Then you plot the zeros, you find that they condense on some curves. And this condensation curve actually is rather interesting from a statistical mechanics point of view. And there are some numerical procedure which you can determine them directly in this n goes to infinity limit, and it matches nicely with this condensation. And for different choices, say you take 16 qubits and 4 magnons, you will get a different pattern for condensation curve. But what's interesting is that it always condense in some curves. So here you are dealing with the result is a polynomial of degree 4,000. So it's some big polynomial and it's analytic, and we have it. Okay. So then you can also consider the Fourier space, which is something like this. And the result is like a rational function. It depends on parameters, say q, which is the exponential eta. And then C, which is exponential U. So U and eta are the parameters that I have in my two-side gate. So you just reparameterize them by Q and eta. And then this A is this exponential minus I omega. So you find this analytic result. Again, is some big polynomial. And then, so this is already for a very simple case. This is just 4 qubits. And then you have this analytic result. So then for more qubit case, we can start to plot. This Fourier space result as a function of omega. And then we can distinguish 2 regimes. So one regime is that this delta, which is my q plus 1 over q, is larger than 1. Traditionally, in the XXZ spin chain language, this is called a massive regime, because in this regime, if you take continuum limit, you got some massive field theory. And in this regime, things become very simple. You just, for example, if you fix the maximum number to be 2, and then you increase this number of qubits, you'll see that they quickly converge. So as the number of qubits increase. That means that if you want to know the result for m equals 2, say to 100 or 200 qubits, you only need to compute actually 20 qubits, because they will converge very quickly. And just to show you how horrible this result looks like, so I take some Q, specific Q and C, and these are like 16 qubit results, you got this. And 4 magnons, you get something like this. So I can show you ever more crazy results. But okay, it's important that it's analytic. It's very, very hard to get these things from doing numerics. And then once you have this, you can calculate as accurate as you want. And these are the number of solutions that we need to take into account in this calculation. So already for 18 qubits, you need to take into account something like around 300 Bethe solutions. Now, in the massless regime, namely this delta, absolute value delta smaller than 1, the behavior is very different. Here, you fix the number of magnons, and then if you increase the number of qubits, you don't see them converge very quickly. Actually,
what's the graph showing?
The graph is showing the following. So I compute this. This is the Fourier space correlation function as a function of this omega. So what is this omega? Let's recall. It's here. This omega.
So the horizontal axis omega
is omega, yes. The vertical line is this. Yes, is the correlation function, the value of correlation function. And you see there are some peaks, which seems to tell you some spectrum of this circuit. And so you compare the plot for different qubits, you don't see them converging like in a massive case. It seems we are seeing that qualitatively a different behavior for the massive and the massless regime. Is there a phase transition? Typically, yes. At least for spin chain, there's a quantum phase transition at delta equals to 1. And then the physics are rather different for these 2 regimes. So yeah, there are a few more plots for 4 magnons. And okay, let me conclude that the correlation functions of integrable quantum circuits can be computed exactly in real space and Fourier space. And we use the technique of Bethe ansatz and the computational algebraic geometry. So in real space, we analyze short and long time behavior of correlation function. And in Fourier space, we analyze different parameter regimes. So in the future, we have a lot to do, like what about other correlation functions, so other strings and other spin operators, or we can consider special parameters. So here I'm taking generic Q. What about Q equals to root of unity? So there are very rich phenomena in this root of unity game. And then there are also some technical issues we need to deal with. And we can also consider some other more complicated integrable circuits. So there are some Cairo-Hubbard integrable circuit, which is also integrable, and we can imagine solving them using similar techniques and explore the physics. So with that, I will end. Thank you very much.
Well, thank you so much for really impressive results here. There's lots of time for discussion, so please. We
could think about the dynamical problem, like for example, suppose you set a special initial condition, like you have a amplitude of only at the origin, and how this state relaxes into that. So can you say something about that?
I see. So what I'm proposing here is a framework, is an analytic calculation framework based on Bethe ansatz and computational algebraic geometry. So in any specific case, if you can say express this amplitude or more dynamical quantities that can be written in terms of beta roots, then we can always do this exact computation.
Yeah, but I guess in such dynamics, you can the distribution of the beta roots can say something. For example, what is there a gap in the spectrum or whatever? So I guess just by looking at the spectrum of the beta roots, you can say something about the dynamics and how you talked about the short-term dynamics, long-term dynamics. What's the behavior? Is there any deviation from the exponential decay? That's my question.
No, here I want to emphasize we are really considering in terms of spin chain language, very short spin chains because we are dealing with 10 to 20 qubits. So for this, we typically need to find all the solutions and sum them over. So if you want to say learn from some specific solutions of beta equations, usually this is done like in the thermodynamic limit. Say in the thermodynamic limit, you can focus on the solution that gives the ground state, and then you can do this 1/L correction. From there, you can extract the information of CFT and so on. So that's the standard practice. So here we are dealing with some slightly different problem. So we really want medium size, not thermodynamic limits setup. And this is because the quantum circuits nowadays we are dealing with is about this range. Yeah, and then we want to actually solve it. Because for thermodynamic limits, there are a lot of tools has been developed. So, but in the medium size, where you need to find all the solutions, this is a difficult case. And we're aiming at this one. Yeah.
Yeah, thank you for the nice talk. So I have a question about the final results. So you already showed the results for a few magnum cases, right?
Yeah.
In such a case, I guess you can store transfer matrix, in the form of the matrix quite easy, right? If you use the sparse matrix. And because the transfer matrix is brought by Pavlov with respect to the magnum numbers. So I'm wondering if you can just do direct computation, for instance, just using mathematical, you can store the transfer matrix for the fixed magnum number sector.
Yeah, so for that we try to compare, say, a brute force results, like what you said, and then the Bethe ansatz calculation. And then because we need to do benchmark, so that we have done. But this method is faster in terms of efficiency. But if you consider very short spin chains, then they are more or less the same, equally the same. But your method, yes, it can work.
So, but by the benchmark, you mean the benchmark by analytical?
Yeah.
You can store the matrix in the. You don't use numerical numbers, right? You're using the.
Yeah.
Okay.
And because we are doing real pure analytics, because we want to study, say, some specific points of these parameters. So we want to get this exact results. So that we avoid doing numerics. So we compare with, if you store this transfer matrix, then this is not numerical matrix. It's going to be analytic expression. So it's somewhat still a bit bulky.
Thank you.
So maybe there was questions during the talk, right, about these physical solutions and descendants.
Yes.
So how is that worked out now?
Okay, good point. So to really eliminate these unphysical solutions, we need to use a reformulation of Bethe ansatz equation. And this reformulation is called the Q system. So it has been developed since 2016. And so we can use this Q system. If you solve the Q system then you find only physical solutions, and this is proven mathematically. So you can get rid of all these unphysical solutions. And also it's more efficient than directly dealing with these Bethe equations. But this part I didn't mention here. So, okay.
Yeah, thanks for a very nice talk. Just wanted to ask a short question. So when you calculated this correlators, you had an initial state choice, which was your domain well, which had the sigma functions, if I understand correctly.
Right.
So is it important that you choose that state, or you could have started from any other initial state?
Let's do parts. We want to choose the state where we can compute this overlap of this state and the Bethe state analytically. So namely, we want to compute it in terms of some nice determinant formula. So domain wall state is one specific state where this can be done. And there's another big family of states, which are called integrable initial states that people usually use in the range dynamics. For those guys, you can also compute that. Yeah. But also it's because this domain wall state is rather easy to prepare. So that's another reason. Yeah.
Those first in the background. Yeah.
Yeah, thank you very much. So yeah, I'm wondering, could we consider to use this technique to calculate the Liebowitz bound in the for some long time or the long range behavior?
I didn't think about that. So what do you have in mind?
This is a short chain.
Yeah, this is a
Short chain, yeah.
So the Robinson bound is, you probably need to consider something very long. But here what we are seeing is just for the short dynamics, we just see this like step by step it spreads a little bit. I don't know whether this counts like a good theoretical upper bound.
I see. So is this, I see. Thank you very much.
So, is your field theory counterpart this computation? And you can try to take the sum down limit, and then you can ask which case. But let's say take the XXX Finchen and 61, and in particular, can you see the peak, the spectrum?
Peak of the, okay. So I can comment on something that's I'm still doing. The field theory counterpart, yeah. As you might know, that this specific circuit can be related to the discretization of sine-Gordon bond.
Yes.
And then you can compute this overlap. So this is, in the field theory case, this is more like a cylinder partition function, where you start with some initial state, you evolve it, you project out. So this is like a cylinder partition function. And in this case, it's related to sine-Gordon theory with integrable boundaries. So the state I start with is no longer the domain wall state. It's more like the integrable boundary state that I was mentioning. And this is supposed to map to some integrable boundary state in the sine-Gordon theory. And then with this overlap, we take the continuum limits, we propose this is a way to compute the exact G function for the field theory. And this is important because if you use TBA to compute the exact G function in sine-Gordon, it doesn't work. So far, the G function computation only works for diagonal scattering quantum field theories. And for non-diagonal scattering, this is still an open question. So using this lattice discretization, this is a proposal for computing the G function. Yeah, so indeed, there are some kind of counterpart like this in the field theory side.
I see. So, for example, you explained many of the signatures, like for example, branch construction of zero you've shown, or the peaks in the spectrum.
Yeah.
Space.
So I don't know how to interpret them now.
I see.
Yeah. It's mainly okay. It can be like if we look at the Fourier space expression, the peaks is somehow means this you have a something very close to this omega. This product is very close to 1. It's related probably to the numerical value of this tau, some spectrum of this tau.
I see. Okay.
Yeah. Thanks for very interesting talk. I'm curious on you mentioned that it is applicable to up to the 10 to 20 size of the system, but I'm curious about what is most time consuming part of your numerical calculation, and how it scale with the system size or some.
That's also
I really want to apply. Yeah, of course. Nowadays, 10 to 20 is reasonable for that. But from service company point, we very curious on such a more larger system size. It is very difficult to be treated in usual events. So yeah.
Yeah. So there are two things. One is so basically two reasons it can become slow. One is the computation of Grobner basis. So if you increase, then you find this Q system that I'm talking about. So it's a non-trivial rewriting of the Bethe equation. You need to work it out. And I think if you reach something like 20, then this equation becomes long, and then it becomes slow. So to improve that, you need to use some other techniques, like putting a computation on some finite field instead of rational number field. So you need some specific techniques to boost that. And secondly, if we emphasize on computing everything purely analytically, then there's some dirty thing hidden is this expression for this tau and the w. So this w takes the form of a determinant, multiply something, and the matrix element of this determinant, they are not very friendly. And then this determinant, so basically you have very bulky expressions, analytic expressions for these guys. So for that, we also need to do something to boost this efficiency. So this is one of our goals to push it as far as we can, and maybe to reach some point where thermodynamics limit is a good approximation, or we can take over. So it has its limits, this method.
I see, but it should be bulky, but the W form of W is systematically obtained from using mathematical or something, or some.
This is something we're trying. Yeah, maybe there are some more simplified expression for these guys. If you write in different variables, it's shorter. And then if you have smarter ways to compute these guys, maybe it's simpler. But in general, if you just split out, it's going to be a big expression.
I see. Yeah.
Last question, Yuval.
Yeah, thank you. So you basically there are many ways of writing a basis. I mean, of course, we can use monomials, we can use all other orthogonal polynomials. Okay, I don't know, sure or whatever. So wonder if there could be any potential boost in this. I mean, of course, Bethe equations are written in very specific forms. So maybe there exists such a orthogonal polynomial that it has nice expressions in it.
Right.
Yeah. So do you think if there's any possible way to achieve that? Because monomial is, of course, the most, I guess, computational friendly choice.
Yeah. So just like our dream. So if someday we have a theoretical understanding how to write down directly the Grobner basis instead of computing them, then it will boost the efficiency really significantly. But this requires another level of mathematical depth. So now it's like you give me a car, I use this car to do something. If you're asking that question, it's like I need to invent this car, or at least I need to deform this car at my will. And this remains still is our dream. And then we really hope that someday we can have a better understanding of the Grobner basis that's specific for the Bethe equations. And for that, we're also discussing with some mathematicians. But it's very important. Yes, it's very interesting.
Thank you so much. Once again, beautiful talk.